Okay. So before I start, does anybody have any questions for me today? No? Good. So today I want to talk about planar graphs, which is actually a research topic that I've been working a lot on lately. So this fits in nicely. But it also means that I'm very close to the topic. So hopefully I don't go too fast and don't skip sort of basic things that I take for granted, but that you guys may not know yet. And let's start with something really simple that I think you've seen before, which is a tree. So a tree is a connected graph with no cycle. And let me write that in a way that also that's equivalent but looks very different. A tree is a connected graph with V vertices and V minus 1 edges. Okay, and just so that we don't get confused, let's say V is bigger than or equal to 1. It's kind of a boring graph if it has less than 1 vertex. And maybe you've encountered this already. I'll use the words vertex and node interchangeably. I tend to say node when talking about trees and vertex when talking about more general graphs, but they mean the same thing to me. Okay, so have you seen this definition before? Either of these definitions? And which one are you familiar with? You can answer in the chat or unmute yourselves and speak. So in particular, there's two definitions of a tree that I've written here. I'm not sure which one you were presented with. So usually the first definition, a connected graph with no cycles, is the thing that acts as the definition. And then you prove that it's equivalent to that second definition, which is a connected graph that has exactly one fewer edges than vertices. So sometimes that second definition is presented as a theorem or lemma. Have you seen that theorem or that lemma? Have you seen a proof of it? Because if not, I'll prove it now. Yes, you've seen it. Okay, good. So that's good. I won't have to prove that. It's a sort of nice proof by induction. Most things that you prove about trees are done by induction. So let's not worry about that, but let's remember these two definitions, and one of them has an important implication, which will come up later. So a tree is a connected graph with no cycle. So if I give you a connected graph that is not a tree, that means that it has a cycle. Okay, so that's the sort of obvious consequence of that. And so that also means, by the second definition, if I give you a connected graph that has V vertices and more than V minus 1 edges, then it's a connected graph that's not a tree, and therefore it has a cycle. nothing complicated. It's sort of a easy consequence of these two equivalent definitions, but it will come up shortly. All right. So that's one sort of basic thing. Another thing we want to look out for, and because I'm not the one who's been teaching this class, I don't know what all the notations you have been using. I suspect that you use capital V for the vertex set of a graph usually, and capital E for the edge set. And I will be talking a lot about the sizes of these sets, so the number of vertices or the number of edges. So I'm just going to use little v is equal to the number of vertices in whatever graph we happen to be talking about, and a little e is equal to the number of edges in whatever graph we happen to be talking about. Okay, and later when we get to planar graphs, little f will be the number of faces. Don't worry if you don't know what those are. I'll define them when we need them. Okay, so here's a useful result. In any graph G, with E edges, the sum over the vertices of G of the degree of the vertices is equal to twice the number of edges. Okay. There's nothing deep about that. So the degree of a vertex is just the number of edges incident to that vertex, right? So in this picture, this vertex has degree 3, this has degree 3, 1, 1, 1, 2, 3, 3, 3, and 1, 2, 3, 4, 5 at this vertex. So the degree that I'm just writing as deg of v here is just the number of edges incident to the vertex. And this sort of easy result just says that if you add up all the degrees, 2 for the 1 right above 5, good catch. If you add up all the degrees, you get twice the number of edges. And why is that? Well, that's because each edge has 2 endpoints. And so each edge contributes once to the degree of one of its endpoints, and it contributes again to the degree of its other endpoint. So really, when you sum up the degrees, you're just counting the edges twice. So, if you call it the left endpoint and the right endpoint, at some point you count the degree of the left endpoint, in which case you count the edge once, and at some point later you count the degree of its right endpoint and count it again. Okay, so twice the sum of the degrees is twice the number of edges. And a concept that we'll use is the average degree, which is twice the number of edges divided by the number of vertices. Okay. So that's typically what we'll do when we do this trick, is to look at this average degree. All right. So let's take a look at the main topic for today, which is planar graphs. And oddly enough, even though it's sort of simple for us to understand what they are, actually getting really formal with the definitions is a bit tricky. You end up having to talk about talk about curves and then define what a curve is, which means you have to talk about continuous functions and so on. So we're not going to do that today. We're just going to work with the intuitive definition, which is good enough for our purposes. So a planar graph is one that can be drawn, like in fact all of the pictures that I've drawn today, with vertices as points and edges as curves, and the sort of only rules are that you're not allowed to have two edges that cross each other. So that means that they intersect somewhere except possibly at a common endpoint. And you're not allowed to do something really silly, which is to take an edge and draw it right through a vertex that's not one of its endpoints. Okay. So the edges are curves that start at one of their endpoints and end at the other endpoint. And they're not allowed to cross like this. Okay. All right. That's clear. Okay. So that's our intuitive definition of planar graphs. And if you have a formal mathematical background, you can define that more carefully. This is a bad example because it has a parallel edge. Let's leave that out. Okay, so that's planar graphs, and an important thing about planar graphs is this notion of faces. So what are these faces of a planar graph? Well, they are what you would get if you imagine that this graph was drawn on a piece of paper, and I took an X-Acto knife and I cut through all of the edges and all of the vertices. So if I did that, then in this picture here, the paper would fall apart into pieces, right? So one of the pieces of the paper would be this one, and another one would be this super light gray one. Another one would be this one. You get another one over here. This would be another piece, and you would get a piece like this. And don't forget, if this were really a piece of paper, there would be one more piece which is this piece here, the whole piece of paper. So the stuff that's the rectangular piece that I cut everything out of. Okay. That thing is usually called the outer face, and all of those other ones are called inner faces. So when I have a planar drawing of a planar graph, then that drawing, I mean, it has edges and it has vertices just like the graph does, but the drawing itself also defines these faces. Okay. So they're sort of an important thing that we're going to study today. And I think you have been shown this before, but never proven it. And that's Euler's formula. And Euler's formula says that if G is a plane graph with V vertices, E edges, and F faces, then E, the number of edges, is equal to the number of vertices plus the number of faces minus 2. And I should not forget, really important qualifier, connected. And another also important qualifier, let's say v bigger than or equal to 1. So it's a graph with at least one vertex. It's connected, and then you get this formula that tells you exactly the number of edges as a function of the number of vertices and faces, or it tells you any one of those three quantities as a function of the other two. So if I were to look at this graph, we should maybe check to see that Euler's formula is correct by at least looking at one example. So let's count faces first. Here's 1, 2, 3, 4, 5, 6, 7. So I get F is equal to 7. Vertices, let's count those. I get 1, 2, 3, 4, 5, 6, 7. So V is equal to 7. And edges, of course, these are the ones that I will for sure miscount. I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So I miscounted something. And what did I not count? Faces, 1, 2, 7, vertices. 6. And there's a vertex that I missed. Vertex number 8 right there. So, and vertex number 9 right there in the center. Okay, so good. And indeed, if we take the number of edges is a 14, that is equal to 7 plus 9 minus 2. So, there it is by example, but of course, example is not how we prove things, at least not in this class. So let's do a proof. As formal as we can do, given that we are working with maybe a not completely rigorous definition of planar graph. So, proof of Euler's formula. So we'll do it by induction. So on the number of edges. And remember that the graph is connected. So it's a connected planar graph. And so if we think about, well, if we're going to do induction, what should the base case be? Well, kind of easy base case is when the number of edges is equal to 0. Now, if a graph is connected and it has no edges, and the careful statement of the Euler's formula said that the number of vertices is bigger than or equal to 1, well, then the number of vertices actually can only be 1. Because if I have 2 or more vertices and no edges, then those vertices are not connected. So in the base case, the number of edges is 0, and the number of vertices is equal to 1. And indeed, and the number of faces, so this is what our graph looks like. It has 1 vertex. I cut a little tiny hole in that thing, and how many pieces of paper am I left with when I do that? I'm left with 1 piece, the original outer face. So the number of faces is equal to 1. And we can check that v plus f minus 2, well, that's equal to 1 plus 1 minus 2. That's equal to 0, and that is indeed equal to the number of edges in our graph. Okay. So the base case checks out. All right. Now we'll do something a little bit funny and not jump to induction right away. So, we've handled the case that there are 0 edges. So let's consider that we have E bigger than or equal to 1 edges. Okay. Now, if E is equal to the number of vertices minus 1. So there's a special case when the number of edges is equal to the number of vertices minus 1. What does that tell us about our graph? So have we seen a special kind of graph that's connected and the number of edges is exactly the number of vertices minus 1? Yes, exactly. It's a tree. So if E is equal to V minus 1, so remember Euler's formula is for connected graphs. So we have a graph that's connected. The number of edges is equal to the number of vertices minus 1. Then G, the graph we're talking about, is a tree. Now, remember, that means that G has no cycles. Why is that relevant? So the graph we're looking at in this case, some nice thing like this, it's a tree. It has no cycles. So I have a graph drawn in the plane, there's no crossing edges, and the graph has no cycles. Well, if we look at what makes faces in a drawing of a planar graph, if we don't have any cycles, we only get one face. We only get the outer face. Okay. So if G has no cycles, that means that the number of faces is 1. Okay. Well, now we know the 3 quantities. We can check that it's true in this case. So if I take so the number of edges, well, let's do it this way. V plus F minus 2. Well, we know F, so that's V plus 1 minus 2. That's equal to V minus 1. Well, look at that. That's exactly equal to the number of edges. So in this case, when our graph is a tree, Euler's formula holds. All right. And now we're almost done. So we now have handled the case when it has no edges. We've handled the case when it has the fewest number of possible edges, just one less than the number of vertices. Any fewer edges and the graph won't be connected. And so now we just need to deal with the case where E is bigger than V minus 1. Okay. So G is connected. But because E is bigger than V minus 1, it has it has too many edges. G is not a tree. It has too many edges to be a tree, but that means G has cycles. It has at least one cycle. I don't know. Let's call it C. So if I look at my graph G, it has some cycle C, and it has lots of other things. And maybe it even has other edges in there and all kinds of stuff. But just what I know for certain is there's at least this one cycle C. I'll highlight it. Okay. Now, take your favorite edge of that cycle. Let's take this one. So there's this edge of the cycle, the edge xy. Now, look at what's happening just around that edge. There's a face on this side of the edge. Okay. There is also a face on the other side of the edge. Now, I claim, and you can check, that those are two different faces. Okay. So let's say on the right side of the edge xy, there's a blue face. On the left side, there's a yellow face, and those are not the same face. How do I know they're not the same face? Well, because xy is part of this cycle C, and the yellow face is inside the cycle, and the blue face is outside the cycle. So if I were to cut out all the edges of my graph, that would include the edges of C. So one of the things that would fall out of there would come from inside the cycle, and the other thing would come from outside the cycle. So those are two different faces. All right. So let's now make a new graph, or a derived graph, that we get by erasing this edge. Okay, so erase that edge. So we'll say let the graph G prime be what happens when you take G and you remove the edge, not E, call it XY. Okay. So some things to note. G prime is connected. You can check that easily. The only danger would be that X and Y were no longer connected, that they somehow fell apart because you took away the edge between them. But X and Y are part of this cycle C, so there's another path from X to Y, not just the edge that we took away. So it's connected. How many faces does G prime have? So remember, G, by definition, has F faces. Now, G prime is the graph that I get when I take away this edge X and Y. Now, XY had two different faces on either side of it, But when I take them away, those two faces become the same face, right? There's nothing separating them anymore, so that they become the same face. So G prime has f minus 1 faces. Okay, and let's call that f prime because it's the number of faces of G prime. G prime has E prime is equal to E minus 1 edges. Right? It's exactly the same graph as G, except I took away this one edge xy, so it has one edge less. Well, since G prime has fewer edges than E, we can apply the inductive hypothesis to it and conclude that E prime is equal to F prime plus, well, how many vertices does G prime have? It has the same number of vertices as before, plus V minus 2. So that's what the inductive hypothesis tells us. But now, what was E prime? Oh, E prime was just E minus 1. What was F prime? Well, that was just F minus 1. The minus 1s cancel out, and so what we get is E is equal to F plus V minus 2. Okay. And that's the proof. So it was by induction on E. The base case was E equals 0. When E is bigger than or equal to 1, there's a special case when the graph is a tree. And otherwise, you can remove an edge from a cycle and apply the inductive hypothesis. So any questions about that just now? Okay. All right. So Euler's formula is really useful. And it's so useful that I want to teach you a trick for how to remember it. I love tricks like this. So let's draw our favorite planar graph, as long as it's connected. So I'm not a big fan of formulas, but I am a fan of understanding things and where they come from. So let's do, I don't know. All right. So there's our favorite planar graph. And you have its favorite connected planar graph. And you have seen, I think, Daryl told you about spanning trees. So this is something, it's a subgraph that you get where you just keep adding edges as long as adding that edge wouldn't make a cycle. And eventually the whole thing becomes connected, and since there's no cycles, it's a tree. So let's just do that. We'll take our favorite spanning tree of our favorite planar graph. All right. So that's one part of that thing, but let's keep a note of that. That is a spanning tree that includes all the vertices in our graph. Okay. So the number of these purple edges, and I'll write it in purple, is equal to V minus 1. Because this is a tree with V vertices. All right, let's look at another object, another graph. And it's the graph that we get when we put a vertex inside each face. And what edges do we put in this graph? Well, don't forget the outer face. Well, we put an edge between two of these vertices. If those two faces share an edge that is not one of those purple edges, so not one of the ones I used already. So for example, the outer face and this one share that edge that was not used in the purple tree. Same thing with the outer face and that one, this one, this one, this one. This one is also shared with the outer face. This one is also shared with the outer face. So is this one, and that's that's all of them. All right, so what kind of thing is this? So what kind of graph is this blue thing that I just drew? Well, I can tell you the number of vertices in that graph is just the number of faces in my original graph. That's the way I defined the vertices of the blue graph, one per face. But what kind of graph is it? Well, if you think about it for a little bit, you'll realize that the blue graph doesn't have any cycles. So why doesn't the blue graph have cycles? Well, what would that mean for the blue graph to have cycle? So if the blue graph has a cycle, that means that the original graph has some edges in it that cross the edges of the blue cycle, and none of them were used in the purple spanning tree. But that doesn't sound right, because the purple spanning tree is supposed to be a spanning tree of all the vertices, which means it's supposed to connect them. And certainly if it doesn't use any of these edges, then, well, the vertices in here won't be connected to the vertices out here. So that's why the blue graph doesn't have any cycles. And why is the blue graph connected? Well, it's connected, you can check if you like, because the purple graph doesn't have any cycles, because it's a tree. So essentially, the blue graph is a tree because the purple graph is a tree. All right, so what? Well, now that we know that the blue graph is a tree, we know the number of edges it has, that's equal to the number of faces minus 1, right? The blue graph, the number of vertices is f, and so the number of edges it has is f minus 1 because it's a tree. Now, the actual number of edges in the original graph, e, well, that's this number plus this number. Why is that? Well, because every edge in the original graph is either a purple edge in the purple tree, or it's crossed by an edge in the blue tree. Okay. So every edge in that original graph, that's what this black E is counting, either corresponds to exactly one edge in the purple tree, in which case we count it in this v minus 1 term, or it corresponds to exactly one edge in the blue tree, in which case we count it with the f minus 1 term. But hold on a minute. That's just v plus f minus 2. So the reason Euler's formula is true is because the edges in your graph that has cycles, they're really the edges of, you can think of them as the edges of two trees. One of the trees is a tree built on the faces, and the other tree is a tree built on the vertices. So you get V plus F, each one minus one for the number of edges. And that's how you remember Euler's formula, and also gain some understanding of it. Questions? Okay, good. All right, so Euler's formula is nice, but number of faces sometimes gets in the way. Sometimes we want something a little more useful that's not so complicated, that just talks about vertices and edges, which are the things we're usually concerned with when we talk about graphs. So here's a consequence of Euler's formula. And here we have to be careful to get all our qualifiers right. Every connected planar graph that has, I'm going to say, E bigger than or equal to 3 edges, and V vertices has number of edges less than or equal to 3 times V minus 6. So often people think of this as the useful consequence of Euler's formula, because it tells you a relation between the number of vertices and edges. In fact, it tells you the maximum number of edges that a planar graph can have. And what's the proof of this? Well, it's really more of an observation. If I have a face in my graph, and my graph has at least 3 edges, then that face has at least 3 edges on its boundary. It could have more, but it has at least 3. Right? It can't have only 2, because only 2 would be this kind of thing. That's 2 edges between the same 2 vertices. So we're not interested in multi-graphs. We're just interested in graphs. So the sort of smallest face you can get has at least 3 edges on its boundary. So every face has at least 3 edges on its boundary. Now let's look at it from the other side. What if I look at an edge? How many faces could it be on the boundary of? Well, it could be on the boundary of one face on this side and a different face on the other side. It's not always on the boundary of 2 different faces. Sometimes those are actually the same face, but it's at most 2. Okay, so every edge is on the boundary of at most 2 faces. So if you think about these 2 statements for a minute, you'll realize something. Well, what do you realize? You realize that the first thing talks about each edge, each face having at least 3 edges. And the other thing talks about each edge being on at most 2 faces. Okay. So the first statement is something about 3f, and the second statement is something about 2e, twice the number of edges. And what they're telling you is that 3 times the number of faces cannot be more than twice the number of edges. So, think of it as sort of the way we looked at the degree sum adding up to the number of edges. It's the same sort of argument, that if we go and walk around each face counting how many edges we see, then we will count each edge twice that way. And on the other hand, if we walk around each edge counting, if we walk around each edge counting the number of faces that we see on that edge, we'll count each face at least 3 times. All right. So another way to write that is that f is less than or equal to 2e over 3. All right. So now we're basically done. We know Euler's formula, which is that E is equal to V plus F minus 2. But now we know F is less than or equal to 2E over 3. So V plus 2E over 3 minus 2. And rearrange that. So subtract 2e divided by 3 from both sides. On the left side, you're left with 1/3 of e. On the right side, you're just left with v minus 2. And now multiply both sides by 3 so that you're left with e and 3v minus 6. And that is this formula here that we're trying to prove. And in fact, it's not just some crude bound. It's exactly the right number of edges. It's exactly the maximum number of edges you can have in a planar graph. In fact, if you just start drawing, draw some vertices and then keep drawing edges as long as you can without getting any crossings, if you started with at least 3 vertices, you'll get exactly this many edges. It doesn't matter how you do it. As long as you do it until you can no longer add a single other edge. It happens when every face has size exactly 3. And those are called triangulations. All right. Good. So here's a consequence of that, which is that every connected planar graph with planar graph G has a vertex x with the degree of x less than or equal to 5. All right, why is that? Well, if I sum over all the vertices in my graph, we already talked about that sum. If you sum up all the degrees, you get twice the number of edges. And that divide both sides by the number of vertices. That's still true, right? Now, by that Euler's bound that we just saw, E is at most, what did I say, 3 times the number of vertices minus 6, divide by V. So you're getting 6V minus 6 divided by V. And well, 6V over V is just 6, but you don't quite have 6V. You have 6V minus 6. So you actually get a number that's less than 6. Okay. So that means if I look at the vertices, on average, their degree is less than 6. But the degree of a particular vertex, any particular vertex, is an integer. So somewhere there's a vertex of degree less than 6, and that vertex that has degree less than 6 must have degree at most 5. Okay. So therefore, some x has the degree of x less than or equal to 5. Has to be less than 6, and it has to be an integer, so it has to be less than or equal to 5. And this particular trick of using the fact that certain things have to be integers and that something has to be less than the average shows up all the time, oddly, in graph theory. So you can prove lots of funny facts this way. Like, first you would look at this and think, where did 5 come from? We've only seen, 2s and 3s, so 6s show up, and all the things we were looking at. Well, 5 comes from this rounding issue. So that's a useful thing. All right. So I believe this is an 1.5-hour class, right? Is that correct? It's not 3 hours per week, or 3 1-hours per week. Okay, good. So we have time then to do a couple of nice things. So one of these will be what I call the 6-color theorem. Okay. So you may have heard of a very famous result called the 4-color theorem. There are even books written about the 4-color theorem. It's one of the earliest examples of a proof that was computer assisted. So way back in the 1970s, 2 people named Apple and Hacken finally completed a proof, but they needed a computer to help them do it. Prior to that, there were many incorrect proofs given by some very good mathematicians. And to this day, so that was in the 1970s, there's still no proof that anybody's really happy with, that doesn't need the help of a computer somewhere. So we won't prove the 4-color theorem today. We'll prove the 6-color theorem. So the 4-color theorem is usually stated as in terms of maps, but as we kind of saw, so maps are basically the graph you get when you look at the faces of a planar graph, right? If you draw a map, what you usually do is draw the outlines of the country. Well, those outlines, they're like, cycles, and the stuff inside is the countries, which is the faces of a graph. And we kind of alluded to it when I showed you this intuition for Euler's formula, that really maps and graphs, they're kind of the same thing. In fact, there's a formal notion of this. It's called the dual, in which the dual graph is the graph you get by putting a vertex inside every face and connecting two of those faces if they have an edge in common. So when we talk about maps and we talk about countries in maps that share borders, or we talk about graphs that have vertices that have an edge between them, it's really the same thing. Okay, so all that to say, well, something people like to do with graphs and maps is to color them. And to color a graph means that you put some colors on the vertices with a restriction that you're not allowed to put two vertices the same color if there's an edge between them. So in this example, I colored the vertices of this graph. This is called a proper coloring, as long as there's no two vertices of the same color with an edge between them. And the four-color theorem says that you can color every planar graph this way using only four colors. So here's an example. I almost got away with three colors on this graph, but I got stuck at the end with needing that fourth color. So that's the famous four-color theorem. It's very difficult to prove and very difficult to understand the proof. So we're going to prove something much simpler today, the six-color theorem, and maybe even the five-color theorem. So the six-color theorem says every planar graph has a proper coloring using five colors. Or sorry, six colors. I'm getting ahead of myself. Okay. All right. So how do you prove this? Well, the proof is by induction on the number of vertices. And if you're going to do an inductive proof, you need a base case. Let's see, what's an easy base case? Well, how about no vertices at all? So if the graph has no vertices, I don't need to use any colors, and I certainly do not have two vertices of the same color with an edge between them. I don't even have two vertices. So that's easy. I love it when the base case is simple like this. So now assume that every graph with v minus 1 vertices has a proper six coloring. Okay. Now, what we just did back here on the previous slide was to show that, let's be careful. Here we showed every connected planar graph has a vertex with degree less than or equal to 5. Okay, so there's this word connected here. We could actually drop that if you think about it for a little bit, if you have a planar graph that's not connected, then really it is made up of disjoint planar graphs that are connected. And actually, each one of those will have to have a vertex of degree less than or equal to 5. So that's fine. We don't need this connected bit, though we didn't bother to talk about it. But we'll use that here. So assume every graph with v minus 1 vertices has a proper 6 coloring. That's our inductive hypothesis. And well, now we have our graph by that previous result. So every planar graph G. So G has a vertex X with the degree of X less than or equal to 5. Okay. So I don't know. Here's that vertex X, let's say. 1, 2, 3, 4. That's 4 is less than 5, so that's a good choice of X. Now, take X away. Take X out of your graph. And that means also take away the edges incident to X. I'm leaving them half in this picture so we don't forget that they're there. Now, that graph has one vertex less. So apply the inductive hypothesis, which says that that graph can be colored with 6 colors. All right, so here it is, coloring of this graph that uses at most 6 colors. In this case, it uses even less than 6 colors. We now want to extend this to get a coloring of the whole graph. So to do that, we have to put X back in. Well, what color are we going to give X? We have to give X a color that is different from the colors of all its neighbors. But X has at most 5 neighbors. So even if every neighbor of X is using a different color, they're only using 5 different colors. And we have 6 colors to work with. So let's take the one of the ones that's not used and use that to color X. So there's the color we can use for X. I know there is one that's free to use because X has at most 5 neighbors and I have 6 colors to work with. Easy. Okay. That's the whole proof. All right, so that's the 6 color theorem. Maybe that's too easy. Let's do the 5 color theorem. And if we're really ambitious, we can do the 4 color theorem. Not really. Okay, now for the 5 color theorem, I need one fact. And the complete graph with 5 vertices is not planar. Okay, that's the graph with 1, 2, 3, 4, 5 vertices and every possible edge. Okay. There's a drawing of it, but it's definitely not a planar drawing. Okay, so question is, why can't we have a vertex that has 6 neighbors? Well, because back here we proved this result, that because the average degree in the planar in a planar graph is less than 6, there's always going to be one vertex that has degree less than or equal to 5. So when we do our coloring, we look in our graph, find that vertex that has degree less than or equal to 5, and that's the one we pick to remove. Okay. So it doesn't work if we just take an arbitrary vertex. Like if I took, well, this graph doesn't have any high degree vertices, but you could easily take a high degree vertex. In fact, even degree 6 would be enough. Inductively color, and then when that comes back, you find that, oh, all my 6 neighbors have different colors. There's nothing left for me to use on this this vertex that I want to put back. So it was by a careful choice of a vertex. Okay, so this important fact that the graph K5, the complete graph on 5 vertices, is not planar. That's important to us. You may have seen it. Another sort of apropos nothing, another obstruction to planarity. In fact, really the only other one is the complete bipartite graph on 3 versus 3 vertices. That's the other thing that's sort of the smallest thing that's not planar. And in fact, in any graph that's not planar, there's a famous theorem by Kuratowski that says you can find these things hiding in there in some sense. So if your graph is not planar, it's because of one of these two things. But this is the one I care about today. All right. So we're going to do, again, the 5-color theorem. Is that every planar graph has a proper 5 coloring. Okay. Proof. So now the strategy that we used last time, just taking a vertex of degree 5, taking it away and coloring, isn't going to do it for us, because when that's done, when the induction returns, or the recursion, if you like to think about programming, when that returns, it could be that all 5 neighbors end up having different colors, in which case there's nothing left for that last vertex, the one that I want to put back and color. So we have to be more clever. But otherwise, things are going to go the same way. We just need to do something a little more clever. Again, it's by induction on the number of vertices. The case of E equals 0 is trivial. Remember, we can color that one with 0 colors, and 0 is definitely less than or equal to 5. And for the inductive step, well, we have a graph with V bigger than 1 vertices. And so we're going to use that result. So we take a vertex X whose degree is less than or equal to 5. So far, the same thing. We find our vertex X. It has degree less than 5. Now, if the degree of X is less than or equal to 4, then we do the same thing as before. So what do I mean by that? Well, if the degree is less than or equal to 4, like in this example here, so big graph with it, we found a vertex of degree 4 in it. Well, we take it away, we color the rest of the graph inductively, And when that's done, we put it back. And since it has no more than 4 neighbors, those 4 neighbors are not using more than 4 colors. So there's a last color remaining. Right? There's a 5th color that we get to use. So that part's easy. Now comes the clever part. If the degree of x is equal to 5, that's the only case that remains. So we didn't get this nice lucky picture here. We got x, and x had 5 neighbors. Now what do we do? Well, we go back and use this fact here. So x has 5 neighbors, and the complete graph on 5 vertices is not planar. So those 5 neighbors, they can't be the complete, I mean, the edges between them, they can't all be there. Okay. So what is that? Another way of saying that, if the degree of x is equal to 5, then x has 2 neighbors, y and z, with no edge between them. Okay. So maybe that looks like this. Here's y, and here is z. Okay. And, you know, there can be other edges, you know, lots of other edges. But the way I picked y and z, you know, maybe all this even, but the way I picked y and z is that there is no edge from y to z. And I know that there are 2 such vertices because, well, those 5 vertices around x, they can't have every possible edge between them. So 2 of them don't have an edge between them. And now let's look at what we do. We have x, we have y, we have z. Let's make our picture as generic as possible. We're going to take this path y, x, z. And this is part of a bigger planar graph. And we're going to take that path and contract those 2 edges. So squish it all down into a single vertex. So what does that look like? So we're going to get a new vertex that we'll call it, I don't know, y, x, z. And everything that was adjacent to y will be adjacent to this new vertex, everything that was adjacent to z, and everything that was adjacent to x. So there were 2 things from above that were adjacent to x, 2 things from below that were adjacent to x. There were lots of things adjacent to y, and there were lots of things adjacent to z. But so we make all of those adjacent to this newly created vertex here. Okay. Now, look at this picture for a few seconds and convince yourself that the graph that we just made is still planar. And I tried to draw it in this picture. The reason the graph is still planar is because this graph was planar. So we were able to draw it with curves for the edges and no edges crossing. Well, the new vertex XYZ that we make, we put it at the same place that X was. So that doesn't affect at all these edges that were originally incident to X. And what about the ones incident to Y and Z? Well, the ones incident to Y used to meet over here at Y. And now you just reroute them so that they just pass really close to where that edge yx used to be. And the same things with the ones in z. So from the planar drawing of the first graph, you can get the planar drawing of the second graph. In fact, if you stood back, it looks exactly the same. I mean, if you don't zoom in on this picture, you wouldn't even see that there's no vertices y and z, because it looks like there's edges meeting there and going off to x. But it is a planar drawing. There's no crossing edges. Okay, so I inductively color this thing using 5 colors. So what happens when I do that? Well, I get some 5 coloring of this graph. I don't know. Maybe it looks like that. And now I want to turn that back into a coloring of the original graph. Okay. So, well, everybody keeps their colors. Every vertex that's in both graphs gets to keep the same colors. But what about y, x, and z? Well, this vertex yxz that I contracted, it got a color. Okay, so that color that it got is going to go onto y, and it's also going to go onto z. Why is that okay? Well, it's okay because there's no edge between y and z. The way I chose y and z, I chose them very specifically so that there was no edge between them. All right. Of course, this is a silly example. X, of course, was chosen so that it only had 5 neighbors. Let's not wreck that. Yeah. So okay. So we're back. Everything is still colored. There's no problems yet, but we haven't colored X yet. Now, X has 5 neighbors. 2 of those neighbors, Y and Z, have the same color. So that means that the neighbors of X are only using 4 different colors. And we finish up by using whatever leftover color we have on X. So using the 5th color there. So that's the end of that proof, and that is also the end of the lecture. And I believe that it is the end of class for you guys. I hope you enjoyed this course, and that you enjoy your summer and do well on your exams. And, you know, maybe we will see each other in person sometime in the next, I don't know, 8 months. Okay. Thank you. Thank you, interpreters. First time I've worked with you before. Good to see. Okay. Goodbye, everyone. Enjoy your evening and weekend.